In this lab, we're going to demonstrate refraction and beam deviation, and we're going to do that using a couple of simple optical elements and some measurement tools. Here we have a red laser pointer, and we have a protractor to measure the angle of incidence and transmission. Here we have a simple ruler and a caliper that we'll use to actually measure the thickness of the optical elements. I'll start by measuring the thickness of the slab. This is a slab optic that has two polished surfaces, an input and an output surface, and 4 ground surfaces for handling. We have a number of other optical elements that we'll talk about in a moment. The slab optic you can align to your laser and center it on the protractor, and then we can watch the beam deviate. Here's the beam transmitting through the optical element. We'll watch the beam deviate on the wall as I rotate the slab back and forth, changing the angle of incidence. And you can see the deviation is larger for larger angles of incidence until I get up to almost 90 degrees. I'll bring it back to 0 degree incidence, and I'll move it back and forth so you can see the spot move from side to side as the beam is deviated with this slab. This is a fairly thick slab, about 30 millimeters in length, and it's causing a pretty significant amount of beam deviation. Here's a thinner slab. It's actually a 2-part optical element, and if we use the parallel slab part of that element, we see less beam deviation. But then if we slide the beam into the wedged part of the optic, we see a significant amount of beam deviation between the 2 parts of the optical element. Here's the parallel, and here's the wedged part, deviating the beam significantly. Another optic you might use to deviate a beam is a right angle prism. This right angle prism is coated on the back surface, so the hypotenuse of that triangular prism is coated with a high reflectance coating, and you can see that the beam is deviated by 90 degrees as long as the incident light is parallel to the laser surface normal itself. And you can also use this as a mirror, a very stable mirror, and this is something you might see used in a pair of binoculars or something similar as a mirror inside of a pair of binoculars to change the image orientation. Another use of a right angle prism is in the Porro configuration, where the input surface is not one of the sides, but is actually the hypotenuse of the prism. If we put the laser beam in the side of the prism, we actually see a beam deviation where the light comes back onto itself, and this is used for lateral beam transfer. So the beam is actually being transferred from this input location over slightly to this output location. So you can see a lateral transfer in this prism of about 10 or 15 millimeters. Another type of prism that's used to deviate a beam by 90 degrees is a pentaprism. A pentaprism has 5 sides to it, 1, 2, 3, 4, 5. And the top 2 sides are the input sides and the output sides of the pentaprism. And as long as you are aligned to the surface normal of the input beam, then the output beam is guaranteed to be at 90 degrees with respect to the input beam. Here we show the principle of beam deviation from above. Moving the slab from side to side, you can see on the output face how the spot moves laterally through the optical slab. With a right prism and Porro orientation, you can see the beam deviation as it goes in on this side and exits on the far side. That's the amount of beam deviation from the right prism and Porro configuration. Here's a right angle prism deviating the beam by about 90 degrees in a mirror configuration. And here's a pentaprism deviating the beam by 90 degrees.